Welcome to ePathshala. This is a series of lectures on computer networks. So, today's lecture will be on application layer protocols. So, we will look at general requirements of application layer protocols, and then we will look at some of the details of the HTTP protocol, the hypertext transfer protocol, which is used for web access. So, that will be our goal for today. So, when we talk of application architectures, as we already mentioned in the previous session, you could either have a client server architecture or we could have a peer-to-peer architecture. In addition to that, we can also have a hybrid of both these schemes, that is a hybrid of client server and P2P. To just give you an example, in the case of a client server architecture, so the situation we have is something like this, that you have a server here and I could have a client which is on some other network or a client on the same network which is connected to this. The server is typically always on, and it could be either a single server or it could be a farm of servers, a number of servers connected together which are present to serve web content or to serve or to provide any service for that matter. Okay. And the reason we use server farms is basically for scaling, that is when you have large number of requests coming in, then to serve those large requests it may not be possible to do it with just a single server. So, you may have a farm of servers. Clients typically, what happens in a client server architecture is that they will contact the server. The server is always on waiting for the client to contact them, and the client may contact the server intermittently, and clients would not normally communicate directly with each other. So, it is always the client contacting the server. So, that is the kind of setup that we have in a client server architecture. If you look at a peer-to-peer architecture, what we have here is there is no always on server. It is arbitrary end systems which just directly communicate with each other, and they do that to share information or for whatever application we have. Okay. So, the peers again are intermittently connected and they may change IP addresses. Example is Nutella, which is used for music sharing. Then you have other such applications which are P2P applications. The advantage of this is that it can be highly scalable because you have a large number of nodes and they could kind of provide whatever service just by talking to each other or just by exchanging information. But there are some difficulties in terms of how you would manage such a network. So, while P2P architectures were thought of as very important and as very that they would really overtake other type of networks, that really has not happened because of the complexity in managing these kind of networks. Another option that we have, as I said earlier, is hybrid of client server and P2P. So, here what you would normally do is this is something which happens in the case of the old Napster application that we had again for music sharing, and then instant messaging also in some cases uses a combination of client server and P2P. So, what happens in this case is that typically if you take an instant messaging kind of scenario, chatting between two users is through P2P, whereas detecting the presence or identifying the location, that is centralized. So, the user would typically register its IP address with a central server when it comes online, and the user will contact the central server to find the IP addresses of its buddies. So, once the addresses are found, then the connection happens by means of P2P and direct exchange of data takes place through P2P. So, here we have a combination of P2P and client server architecture. Now, given that we have these three different types of applications as such, we also talked about different types of services that a network has to provide for these applications. So, let us look at these applications from that point of view as well. That is, what kind of transport service would an application need? Now, remember that your application runs on top of the transport layer protocol. So, we are basically looking at what kind of service the transport layer should provide, or in other words, given that we have an application, what kind of which transport protocol should be used for that particular application. So, again as we see, there are three parameters that we normally look at. One is data loss, the other is bandwidth, and the third one is delay. So, again if you look at different applications, some applications can tolerate delay, some applications can tolerate data loss. So, we talk about loss tolerant versus delay tolerant applications. So, if you take applications like audio for instance, they can tolerate some loss, and whereas other applications, for example like file transfer, would require about 100% reliable data transfer. Now, similarly if you take bandwidth, there are applications like multimedia which require minimum amount of bandwidth to be effective, whereas there are other applications which are called as elastic applications which can make use of whatever bandwidth they can get. Email for instance would come under an elastic application. Again, when it comes to delay, there are applications like internet telephony and interactive games which require low delay in order to be effective, whereas other applications like email or file transfer can tolerate delays. So, given that we have these different requirements for different applications, let us just kind of summarize some of these numbers that we have for these particular applications. So, if you take the set of applications that we have here, starting from file transfer, to instant messaging, we are looking at data loss, what kind of bandwidth requirement it has and how sensitive it is to delays. So, file transfer, if you say you cannot tolerate losses, so we do not want losses, and but bandwidth can be elastic and it is not delay sensitive. Email similarly is not cannot tolerate losses, elastic, not delay sensitive. Access of web documents is also similar, but if you take real time audio or video, it is loss tolerant, but it requires a certain amount of bandwidth and again is also sensitive to delay, right. So, audio for instance may be 5 kilobits per second to 1 megabit per second, video would anywhere in the range of 10 kbps to 5 megabit per second. Similarly, stored audio or video, again it is loss tolerant, bandwidth requirements are about the same as real time audio video, but it is also delay sensitive, but can tolerate a certain larger delay, because since it is stored audio video, you can always adjust your playback accordingly. So, interactive games, again if you see, it is very similar to the case of real time audio video. So, it is loss tolerant and requires few kilobits per second, and the delay again would be of the order of about 100 milliseconds. If you take instant messaging would be no loss, it is elastic, and with respect to delay you can say it is yes and no, because it is, you can tolerate certain amount of delay, but if the delay is too high then a user may not be able to tolerate it. So, given that we have these service requirements and given that we know that there are two types of protocols which are used at the transport layer in the TCP IP network in the protocol suite, we have TCP protocol and UDP protocol. Remember that TCP is a reliable protocol, whereas UDP is not reliable, but can provide you fast service. TCP incurs certain delays. So, given that these are the typical underlying protocols which are used for these different applications, and I am also mentioning the application layer protocol that is used for supporting these applications. So, if you take email, the application layer protocol we have is SMTP and the underlying transport protocol used will be TCP. So, because we said that this cannot tolerate losses. So, you can see that all the applications which require no losses will typically use TCP. So, you can see that email, remote access, web access and file transfer, they all use TCP as the underlying transport protocol. Streaming multimedia, application layer protocol, normally we have some proprietary protocols like real networks which are used for this. It could use either TCP or UDP. Internet telephony typically uses UDP. Examples are proprietary protocols that used for internet telephony are like Skype, plus there are other standard protocols also which are used like H.323, RTP, SIP, etc. We will look at these protocols later, but these are the kind of protocols that are used for these kind of applications, and this typically internet telephony typically runs on top of UDP. And when I have given these application layer protocols here, we also talk about something called an RFC. RFC is a request for comment, and in the network arena typically most of the standards for the protocols are standardized by means of these RFCs. So, when a new standard is to be floated, it is normally put out as an RFC, and once which means you are basically requesting for comments on that particular proposal, and once the proposal is examined by others and is proven to be a viable option, then that becomes the standard itself. So, you can see that most of the protocols which are used in networks will be given in terms of RFCs. Okay. Now, coming to application layer protocols and trying to understand what is required from for an application layer protocol. So, an application layer protocol would define the following. One, it will talk about the types of messages exchanged, example what is a request message, what is a response message and so on, and the syntax of these message types. So, what are the fields in each message and how these fields are delineated. And of course, we also need to understand the semantics of the fields, that is the meaning of the information which is there in the fields, and rules for when and how the process send the messages and respond to the messages. So, all these you will find are given in any application layer protocol. So, what we will do now is that we will start looking at some application layer protocols in this and the next 2-3 sessions. Examples of application layer protocols, as we said, for web access we use HTTP, for mail transfer we use SMTP, and there are many proprietary protocols also which are used. Now, the proprietary protocols may not be available as RFCs, but public domain protocols are available as RFCs. So, what we will now look at is the most popular protocol or the protocol used for the most popular application, which is web access. The protocol used for web access is HTTP or the hypertext transfer protocol. So, before we start with the HTTP protocol, let us just start off with what we mean by accessing a web page. So, what is normally a web page? A web page basically consists of some objects. So, there will be a base HTML file which will include several referenced objects. one or more reference to objects could be there. And each of these objects is addressable by means of a URL, okay, a uniform resource locator. And these objects that we are talking about could be any type of file, it could be a HTML file, it could be a JPEG image, it could be Java applet, it could be audio files, video files and so on. So, a URL typically looks like this, is something that all of us are familiar with. You have the host name, so something like www.someschool.edu, and then the path name which specifies the object. So, some department / pic.gif and so on. So, to start with, to give an overview of HTTP protocol. So, you will have a HTTP server or the web server which will be running the server part of the protocol, and you will have different clients which will talk to the server. So, the communication between the client and server happens by means of the HTTP protocol. So, we talk about HTTP requests and HTTP responses. So, the client is the one which sends a HTTP request to the server, and the server responds with a HTTP response. So, this is the model in which HTTP works. When we talk of HTTP protocol, the standards used again is mentioned in terms of RFCs. HTTP 1.0 is given in 1945, and HTTP 1.1, which is currently used is defined in the RFC 2068. Okay. So, you can have different clients running these different the client programs. There is different machines could be running these client programs. It could be different types of browsers which are running these client programs, the HTTP client part, but all of them should be able to talk to the server. Okay. So, that is the requirement that we have. So, it could be any client machine which should be able to talk to the server using the HTTP protocol. So, the protocol has to be defined in such a manner. So, HTTP, as we said, will run on top of TCP because we require reliable access, and it normally connects to the server at socket number using some kind of a socket interface using TCP sockets, and it connects at port number 80. Port number 80 is the well known address for web servers to run. So, because we said that servers will be running at a particular location, and the clients must be able to contact it. So, the clients must know which is the port at which the servers run. So, web server always runs at port number 80. So, so the client will establish a connection to port number 80. Then the server will accept the TCP connection from the client, and once that is done, HTTP messages can be sent from the client to the server, and after that the TCP connection will be closed. Now, there are certain interesting points to note about the way the HTTP protocol itself is implemented. Okay. So, one of the important things that we have with the HTTP protocol is that it is a stateless protocol. Now, what we mean by this is that the server maintains no information about past client requests. So, every request is treated as if it is a fresh request. So, there is no state maintained as part of the HTTP protocol. Okay. The reason HTTP is designed to as a stateless protocol is that if you have protocols which maintain state, then the complexity of those protocols increases quite a bit. Okay. So, because you have to maintain all past history, which means you have to maintain past state, and if a server or a client crashes, then their views of the state may be inconsistent. That is, the server may be in a different state and client may be in a different state. So, if they are in inconsistent states, then reconciling that would also be difficult. So, which is, and HTTP, since is expected to be a very robust protocol catering to different types of clients simultaneously accessing the server, it has been designed to be a stateless protocol to maintain that kind of simplicity. Now, when we talk of HTTP connections, we said that a connection will be established and then an object will be requested. So, we also said that a single page could contain multiple references to multiple objects. So, in that case, how exactly do we get all these objects which are there in a single page? So, if you look at that, there are two options that we have in HTTP, one called non-persistent connection and the other called persistent connection. So, when you have a non-persistent connection, what we do is there is only one object that can be sent over a TCP connection. At most, one object can be sent over a TCP connection. Our older protocol, that is the HTTP 1.0 version, uses non-persistent HTTP. So, in this case, what would happen is that for every request, that is, once you get the first to send out your first main page, you would have sent out one request, that happens on one TCP connection. Then once you identify that there are a number of objects to be retrieved in that particular page, for each of those objects a fresh TCP connection has to be established, a connection request has to be sent, and then the request for the object has to be sent, and then the object will be served from the server. So, for every object there will be a delay. Now, persistent HTTP on the other hand allows us to speeden up the entire process. What this allows us to do is, once a TCP connection has been established between the client and the server, multiple objects can be sent over the same connection, right. So, that is, once you have the first main page that has been obtained on a particular TCP connection, you can use that same connection to request for other objects which reside on that same server. Okay, so that is the idea that is used in persistent HTTP. So, what we do here is that we reduce the overhead of every time opening a connection and closing a connection. By default, HTTP 1.1 uses the persistent HTTP, and by default it uses persistent HTTP, which means it can also work in non-persistent HTTP mode if the client or the server does not support it. So, if you look at the non-persistent HTTP, let us say we have a web page which contains text plus some 10 references, that is that references to 10 different objects. So, let us look at the steps that are involved in this scenario. Okay. So, the user enters this URL some school.edu/some department/home.index. Now, the first step that we have here is the HTTP client, which is the browser basically, will initiate a TCP connection to the HTTP server at www.someschool.edu on port number 80. Okay. So, once that is done, now the server which is running at this particular host is waiting for this for a connection at port number 80, will accept this connection and send back a notification to the client that it has accepted the connection. Once this receives the accept message, then HTTP will send a request message which contains the URL, which contains this complete information of which page is being requested into the TCP connection socket. So, the message will indicate that the client wants this particular object. On receiving this message, now the server will process that request message, form a response message which contains the requested object and sends the message back to the client. Once that is done, once the response is received, now the HTTP client will receive the response containing the HTML file and display the HTML file. Now, on passing the HTML file, it will find that there are 10 referenced JPEG objects. So, now what will it do now? It will repeat the same steps 1 to 5 for each of these 10 JPEG objects. Okay. So, you can see that the same process will be repeated for every single object which is there in that particular page. So, if you look at the amount of time that this will take, okay. So, let us look at how we can find out the total time that it takes for obtaining a web page. Now, normally we make use of a term called RTT or round trip time. Okay. So, what we mean by round trip time is the time that is taken to send a small packet to the time taken for a small packet to travel from client to server and back. Thus, I am sending something from the client to the server and maybe a response or some kind of an acknowledgement comes back from the server to the client. So, this we call as one round trip time, okay, time it takes from client to server and back from server to client. Okay. So, in the case of non-persistent HTTP, so let us look at how much time it takes to retrieve a single object, because we saw that if there are 10 objects, it will take 10 rounds of processing for us to retrieve those 10 objects. So, let us look at the time taken for a single object. For a single object, if you look at, we first of all have to as we saw, we have to first establish a TCP connection, that will take up 1 RTT. Okay. So, then we are sending the actual request for the file and the file has to be sent back from the server. So, that will take up another RTT. Now, what we also have to understand is if the file is big, it will take a certain amount of time to transmit that file. Okay. So, there will also be some finite amount of transmission time. So, if you look at the total time that is taken, that is the time taken for you to receive the file, so that you can start displaying it, it will be 2 times RTT plus the transmission time. Okay. So, once you have done this, then we close the TCP connection, so which means it will take up 1 more RTT. So, it will take up altogether 3 times RTT plus transmit time for retrieving a single object. So, in the previous example that we saw, if we had 11 objects, so what would happen is that it will take 11 into 3. So, 33 RTTs plus the transmit times for the entire page to be retrieved from the server. So, the major problem that we have with the non-persistent HTTP issue is that this additional overhead that we have for each TCP connection. Now, what we also have to understand is that there is also an operating system overhead which will be there for a TCP connection, because for every TCP connection that is opened and closed, there will be some amount of processing that needs to be done from the operating system point of view. Okay. So, the solution to this that browsers normally employ in order to speed up the entire process is that they could do one of two things. One is that they could open parallel TCP connections to fetch the referenced objects, because remember that once we have opened up the first page, we have got references to 10 different objects. So, now we know the URLs of all the 10 objects. So, we can parallelly open 10 different TCP connections and have them processed in parallel. So, that is one option. The other option that HTTP itself provides for is our persistent HTTP. So, what will happen in persistent HTTP is that, as I mentioned earlier, the server will leave the connection open after sending the response. So, the server will not close the connection, okay, so that the subsequent HTTP messages can be sent over the same connection as long as all the messages are to the same server. Okay. And again, when we talk of persistent HTTP, there are again two options that we have. One is called as persistent HTTP without pipelining and persistent HTTP with pipelining. So, what we mean here by without pipelining and with pipelining is that when we do not do pipelining, what we will do is we use the same open connection, but we issue only one request at a time. That is, let us say we are having 10 objects that we have to retrieve. So, I give the request for one object, only after receiving the response for that object I will give the request for the second object. Okay, so, you have to wait for at least one RTT for retrieving each referenced object. When we use persistent HTTP with pipelining on the other hand, what we do is, since we know that these are the 10 different objects to be requested, we send a request for all the 10 objects one after the other, that is back to back we keep sending the requests. So, what will happen then is the requests reach the server very soon. So, in almost just about 1 RTT or just about little more than 1 RTT, all the referenced objects can be retrieved. Okay. So, we will have a situation which is something like this. So, if you look at the response time, so let us say for instance in this example, there are 3 objects which are there in a main page. So, if you look at this scenario, if it is persistent HTTP without pipelining, so what we will do is we will first open the connection, that takes up 1 RTT, then the request for the main page, right. So, that takes up another RTT. Then once you have got that, you will send the request for the first object, get the object, then send the request for the second object, get the object, then send the request for the third object, get the object. Once all these have been obtained, you can close the connection. So, you can see that it takes up 1 for connection open, 1 for main page, 3 for the 3 objects. So, 5 RTTs plus 1 to close the connection. Whereas, if you did persistent HTTP on the other hand, so look at what will happen here. So, I will first open the connection, then send the request for the main page. I have got the main page. Now, as soon as I get the main page, I know that there are 3 objects in it. So, I send all these 3 requests back to back, right, one following the other. So, in a pipeline manner. Now, the 3 responses also start coming in a pipeline manner. So, in just about 1 RTT, I get back the response for the for all the 3 objects as well. So, the total time that it take will be 3 RTTs to retrieve all the information that I have for the in the web page plus 1 to close the connection. So, given that now that we have understood the different manners in which the HTTP connection works, now we will take a look at the request and the response messages and their formats. Okay. So, there are as we said 2 types of HTTP messages, one the request and the other is the response. Okay. So, if you what is very interesting to note about many of these application layer protocols is that they are all sent as ASCII messages, that is they are all in human readable format. So, if you look at the message, you can clearly see what is the information that is being sent as part of this HTTP request message or what is obtained as part of the HTTP response message. So, this is basically what a message will look like. Okay. So, the first one that you have will be the request line, which has some command that is specified, get, post, head and so on, followed by the URL that you are trying to get from the server. Okay. It also be followed by the version of HTTP that is being used, so that has to be specified. So, this will be the first line that we have. This is the request line. This request line can be followed by 1 or more or 0 or more header lines. There could be many other header lines that are specified, which give more information about the kind of request that we have. Okay. So, we have things like user agent which specifies which is the web browser which is sending this request, okay, and whether you want to have it as a persistent connection or a non-persistent connection. So, you can say connection close, which means that once this object is served you can close the connection, and what is the language in which you want to accept the web page. All these are kind of information that could be obtained that you can specify as part of your request message. Okay. And then once you have done this, you end the entire message by giving a carriage return and a line feed. Okay. A carriage return, that is just an empty line with carriage return and line feed, acts as the end of the message. This is how a HTTP request message will look like. So, the general format is like this. You have the method specified space, URL, space, version, and each line will end with the carriage return and a line feed. Okay. Then you have different header fields, header field name, colon, value. So, that is the format in which it is specified, and each of this header line again will end with the carriage return line feed. Now, these are optional, and then once you have ended this header part of the message, there is a carriage return line feed, and if there is some body of the message, that is if there is some information that is also being sent as part of the request message, then that will be followed, that will follow this carriage return line field, and the whole thing again will end with the carriage return in a line field. Okay. So, this is basically what your HTTP request message will look like. The different methods that we have here, more methods supported in the HTTP 1.1 version than in HTTP 1.0. HTTP 1.0 typically we have these methods like get, post, head and so on. Get is used to get information from the server. Post is used when you want to send some information to the server, you want to post information to the server. For instance, in the case of using forms and so on, we could post information to the server. So, in those cases we use post. Now, head is something which is used only to retrieve the header from header part of the object. We are not asking for the entire object, but only the header part of the request message or the response message alone is requested. So, that is head message. In the case of HTTP 1.1, we have these basic get, post and head methods. In addition to that, there are methods for like put, delete, connect, options, trace and so on. So, put is used to upload a file in the entity body to the path which is specified in the URL field. Delete again is used to delete the file which is specified in the URL field. Connect is used when you connect, when you are establishing some kind of a tunnel between one server and another server. You can also use something called tunneling, which is supported in HTTP 1.1. And options and trace are again other additional things we use for debugging purposes in HTTP 1.1. Now, we said that we do not that a request message can be used not only to get, but also to post information. So, if you post information, you can see what is happening in the case of a post. A post method, the web page, there are two ways in which post can be done. One is using the post method itself. So, for instance, the method that is specified here, the method would be specified as post, and the information that you want to post will be sent as part of the entity body. The other option that we have is you could use the get method itself, but in that case the information that you want to send is added to the URL part of the request line. That is, you have a get with somesite.com something plus whatever information I want to send is also sent as part of the URL itself. So, this is another method by which you can upload data to a server, okay, send data to a server through a form or whatever purpose. So, next if you look at the HTTP response message, right. So, this is we looked at a request message, now we are talking about what a response message will look like. So, if you look at a response message, you can see that the response will have again first a status line which indicates a version part and then gives a status code and a status phrase. Okay. So, this is what you have as the first line. Again following this there are multiple header lines which give a lot of information about the response, and then that is followed by the actual data. Again the header line will end with a carriage return line field or a empty line, and then the data will follow that. Okay. So, this is what you normally have in the case of a response message. So, you can have things like connection close, you will have dates, the server which is returning the message for you, the date at which this particular file was last modified, length of the content, type of the content and so on. The response status is very important because that is what tells us whether the whole request has been successful or not. So, normally it is a 3-digit number. So, 1xx indicates informational, it is just an indicational, just gives you some information. 2xx always indicates success of some kind. 3xx redirects the client to another URL. 4xx indicates an error on the client's part. 5xx indicates an error on the server's part. So, these are some of the commonly used status codes that you may be familiar with. 200 is used for OK, 301 moved permanently, 400 bad request. Now, 404 not found is something that all of us would have come across quite often, and 505 HTTP version not supported and things like this. So, we saw that there are many header lines in both the request and the response fields and the headers, right. So, these there are a lot of information that can be specified as part of these request and response headers. So, we have things like accept character set, accept encoding, accept language. Many of these you can see are self-explanatory. It tells you which kind of character set will be accepted, what kind of encoding will be accepted, what language will be accepted for the request and so on. Authorization can be specified from the host from which you are expecting something, from which you are expecting this information. There are also other things like you can specify, for instance, things like you are expecting the page to be fetched only on certain conditions. So, for specifying those conditions we have things like if match, if modified since, if none match, if range, if unmodified since and so on. So, these are all different conditions that can be specified which will be used in what is called as a conditional get message. So, you can have specify conditions when you are doing a get, when you are getting the message itself. Similarly, there are things with respect to how many proxies or intermediate servers can be allowed between the client and the server. So, we talk about maximum forwards, and if you are using a proxy server, then what kind of authorization can be done for the proxy. So, all these are different headers that you have in the request message. Similarly, in the response messages you have things like accept ranges, age, e tag, which is a kind of an entity tag which can be used for matching some entities, and then location, proxy authenticate, okay, server, vary. There are a number of such header lines which are specified as part of the response message. Now, one of the things that you could do to understand how this HTTP work is that you can actually directly be the client side of the HTTP protocol itself. How you do that is that you just telnet to any web server and do a telnet, specify the web server name and specify the port name. Okay. So, for instance, in this case telnet cis.poly.edu is the name of a educational server. You are telnetting to port number 80, which means you are connected to port number 80, that is you are actually establishing a connection to the web server running at this particular on this particular server on this particular machine. Okay. So, now then you can just specify your HTTP request. So, get say slash tilde ROS slash HTTP slash 1.1, which is you can see get space, then you have the file name space version of HTTP, and then the second line is host, you specify the host name, and then you end it with the carriage return and a line field. Okay. So, once you hit carriage return twice, that is one will end this line and then you will end the message itself, you will look at the complete response message which is sent by the HTTP server. So, that is this web page, the index.html which is there at this particular website will be returned to you, will be displayed on your terminal as part of your telnet screen itself. So, this is just by giving this different headers you can actually figure out what are the different responses that will actually come from the server. So, this is one of the easiest ways in which you can learn the HTTP protocol. So, to summarize, what we have looked at is different types of requirements that different applications have, and we have looked at the HTTP protocol which is used for World Wide Web access, and as part of the HTTP protocol we have looked at different types of connections that we have, request response messages. So, other details of HTTP protocol can be looked at later. Thank you.